And so any other questions before I just jump into the review? Because the review section does have some of the math questions, and it's usually the math questions like the sizing of the arrays, the string calculations, voltage drop calculations. That's usually what people get a bit concerned about. I don't think any part of it is difficult, but there's just so much to remember that it can be problematic. So any questions before I jump into the review? We're still on chapter 7. So
I guess also quickly for the string calculations and the differences in voltage, where do you find the hottest and coldest days data?
yeah, you'd have to, typically I'll just take the zip code or the city location and do an internet search. You can find them online.
Okay.
You may have to do a conversion from Fahrenheit to centigrade or Celsius, but that's not that difficult either. There are online tools for doing that. Now, in a question environment like on the test, those would have been given to you. So,
Sure.
so that would be, you wouldn't have to do that kind of search. But those calculations are available, or those numbers are available online. And it does mention in the textbook too, there is a provision within the National Electrical Code that says you can use that factor table for calculating the impact for lower temperatures, but only if you do not have access to the specification sheet of the panel itself. So there is sort of a fudge factor way of doing it. But in the world of today with the internet access, there's really almost no case where you cannot just simply look up a spec sheet on a solar panel. So even though that table still exists in the NEC, it's almost never used because, I mean, a good electrical inspector would not allow you to use it. And it's not as accurate as doing the temperature coefficient times the number of degrees delta between coldest temperature and actual STC temperature. Okay, so jumping in, if the voltage drop of a system is too great, what can a system designer typically do to fix this problem? Increase the capacity of the battery bank, incorporate a voltage diode, increase the size of the wires, or increase the maximum power point tracking setting. I'll wait for someone to shout it out.
Wire size.
Yeah, it's going to be the wire size. Typically, the options are going to be shorten the distance, but normally you're going to have already designed it to be as short as possible. Oh, I clicked the wrong button. Yeah, okay, well, that's good that it told me I was wrong. You can adjust the wire size, shorten the distance, use a better wire, usually copper versus aluminum, or increase the system voltage. Which of the following is considered the maximum current a panel can produce under standard test conditions?
Opens.
That's ISC.
Yeah, the short circuit current. So that's and the reason we use that is we use that in calculating our wire size. That would be the worst case scenario, the amount of current that would be handled if it were short circuited. You've installed an array of 24 panels, each with an IMP of 8.35, and it's been configured into 4 strings of 6 panels. Assume that the PV source circuit wiring has been placed in a conduit that's exposed to sunlight and is mounted directly on the deck of the roof. These conduit runs run to a combiner box that's mounted on the north wall of the home, so it's never exposed to sunlight. What is the minimum ampacity rating of each circuit breaker that is connected to each PV source circuit within the combiner box? So let's assume, I don't know if I have a sheet of paper here. I should have. If you guys can remember these numbers, We've got 4 strings, 6 panels, 8.35. So if I go out here and go to the whiteboard. All right, so we're saying we have, what did I say, 4 strings? And it was 8.35
Yep.
amps. And what it's saying is, okay, these are combined. And, oh, the combiner box, these are in sunlight here, but the combiner box is in shade. So what would be the ampacity of each of these strings? Well, we take this times 1.25, which would be the NEC adjustment. And then we'd multiply it again times 1.25, which is the solar variability adjustment. And we end up at 8.35 times 1.25 times 1.25.
Well, so
So like 13.05.
Yeah, 13.05. So each of these strings is going to be about 13.05 amps. So now it's saying, okay, well then if we're hooking up each of these to a circuit breaker, what size circuit breaker are we going to be hooking up in here?
it's like a 15.
Yeah, you go to the next available. So it's going to be a 15 amp breaker. So you basically have 4 15 amp breakers in your combiner box. Now, all of that discussion about exposed to wire and all of that, that's a red herring because it would affect the size of the wire, but it doesn't affect the breakers because the breakers are not in the sunlight. So the answer in this case is going to be 15 amps. So an AC disconnect should comply with all of the following except isolate the PV system from the grid, be located at least 10 feet away from the point where the PV system connects to the grid, be externally operable, or be clearly marked distribution generation disconnect switch.
And feet.
Is it 10 feet? Yeah, yeah.
It's got to be located within 10 feet, not at least 10 feet away. All right, when an unintended pathway is created between a PV array and a grounded surface, this is known as?
Fault.
Yeah, it's a ground fault. So basically you're giving the grounding system is designed to take any current that's created in a ground fault and run it to the ground rather than go through your body if you touch that piece of metal. A charge controller must be compatible with all the following except the battery bank's nominal voltage, the array's nominal voltage, the inverter's power rating, or the array's output rating.
So is the battery bank's voltage?
Yeah, let me show you. It makes more sense if you think about how these things fit together. So let's say this is your array here. We're going to go to a junction box, a DC disconnect. Then we go to our charge controller. Then we go to our battery bank. And from the battery bank, you go to the inverter. From the inverter to an AC disconnect. And then to your load center. Okay, so it's saying the charge controller's got to be compatible. Well, what does it have to be compatible with? The only 2 things it touches are the array and the batteries.
Mm-hmm.
It doesn't care if there's an inverter even present.
Sure.
This could be a complete DC system. So the only thing we have to worry about to be compatible with is either the battery bank or the array. So in this case, the inverter's power rating in watts is a non-issue. And the inverter's power rating is going to be dependent upon, in a standalone system, the maximum power draw from your loads. So your inverter has to be able to deal with the loads. So remember I talked, or if you were on the call last Thursday, talked about how the system is really divided into two parts. There's the array to the batteries, that's standalone, and then there's the batteries to the load, and that's standalone. Neither one is dependent on the other one even being present. Of course, without them both being present, the system doesn't make a lot of sense, but you would be able to charge your batteries from the array, and you would be able to run your loads from the batteries for a short time anyway. To account for the inefficiencies of a PV system as the result of voltage drop, loss due to connections, inverter inefficiencies, inverter battery load resistance, etc., you must what the estimated power output?
D-rate.
Yeah, so the D rating is basically all of the inefficiencies that are built into the system. A load diverter reduces the system load demand when the array is not generating enough power, redirects excess power to the grid for net metering through the grid-tied system inverter, reduces the load from the array so the battery does not overcharge, or redirects excess power from the array to a load dump, such as a hot water heater.
Is it the load dump?
Yeah, the load dump, a load diverter. So essentially what that's saying is in a grid-tied system, you don't have to worry about load dump because all the power that's generated, if you're not using it, it's going to the grid and you get credit for it. But in a standalone system, assuming you don't need the power, but the power could still be generated, unless you have some place for it to go, nothing happens. Well, it doesn't hurt the system, but it's an economic opportunity cost that you could be generating power, but you're not. So what they do typically, and usually in a standalone, they'll then run a DC electrical heating element to a hot water heater. The hot water heater itself is not going to be electric. That's just too big of a load for a small standalone system. It might be gas or it might be wood, but then your excess power from your array is at least being used for something. It's offsetting the cost of natural gas or the cost of wood for the hot water. The maximum DC nominal voltage and accessible battery bank within a residential standalone system in the US can be configured to by code is, there's a lot of qualifiers there.
In the
So for battery banks inside residential homes in the US, what's the maximum voltage?
I don't know, I have to go with 600.
Yeah,
yeah, 50.
it's 50 volts. Now, it used to be that was all, no battery bank could be more than 50 volts, which basically meant a 48 nominal volt system. But now they've recently changed the code to say if the batteries are inaccessible by the homeowner, essentially a trained technician has to be able to open up the box and get to them, then the voltage can be unlimited. So what you've seen is a lot of battery banks now coming out, like the Tesla Powerwall, those kind, that are at 400 volts, maybe even more. That reduces the cost of the batteries because you can get by with a smaller wire. But it also, if you think about, if you've got a 400 watt or a 400 volt array hooking into a 50 volt battery, you've got to reduce down the voltage in the charge controller from 400 to 50. Well, there's some loss when you do that. So if you could come in at the higher voltage, then the system losses will be reduced as well. So there are some advantages to it. Which of the following is not a circuit in a typical grid-tied PV system?
Is it PV input?
PV and
Yeah, it's the PV source is the circuit that's between the panels and the combiner box or the junction box. Then from the combiner box or junction box to the DC disconnect is the PV output. From the DC disconnect to the inverter is the inverter input. And then from the inverter to the load is
Right.
the PV output circuit.
I think you drew that one up in last week's.
Yeah, yeah. I always say the PV input is the sun. So that's the input
Right,
circuit,
right. Yep.
then the source circuit. When sizing a battery bank, its storage capacity is measured in,
Amp hours.
yeah, amp hours typically. Although with the lithium ion batteries, they usually don't refer to the amp hours anymore. Now they'll just refer to kilowatt hours. So this is really a deep cycle battery thing. Yeah, for lead acid. Which of the following is not an advantage of microinverters over string inverters? No string calculations required, they're easily accessible, they're more efficient, or they reduce aging panel mismatch.
Um, are they more efficient? I don't think they're more efficient.
Yeah, usually they are. Often they're not as easily accessible for repairs because they're under the panel. But there are no string calculations. Of course, it's usually
Right.
a one-to-one. They're usually a bit more efficient because they're smaller, they are solid state, they don't require a cooling fan of any sort, which often increases the inefficiencies. And of course, they do aging panel mismatch. This is getting a little obsolete now that we have um, power electronic, module level power electronics, even with string inverters.
So what is it? Why would they be less accessible? Is it just because there's more of them, so you'd have to access each individual one, or?
Yeah, well, if you're going to repair a string inverter, usually that string inverter is located in an accessible, dry location where you can stand there and pull the cover off, like in a basement or a garage. Where a microinverter is going to be under the panel, up on the roof. So you got, and of course, the one that broke that you got to get to is always in the middle of the array. So you got to
Sure.
move panels to get to it. If it's a ground-mounted system, then that may not be the case because you can get to a ground-mounted system pretty easily, but
Got it.
still not quite as easy. And it usually happens on a cold, rainy day. Okay, which of the following is not a factor to determine the size in amp hours of a standalone system's battery bank? Daily system load, the nominal voltage, peak sun hours, or depth of discharge?
Like sun hours.
Yeah, because we use like days of autonomy. We don't use the insulation um, when determining the battery bank. Actually, I was just reading a thing about some lithium ions. Many of the lithium ion systems now will go to 100% depth of discharge. So that's a real advantage with the lithium ion batteries versus the lead acid. All right, the maximum DC voltage a grid-tied system in the US can be configured to by code is?
That was 600.
Yeah, that's 600 volts. And we keep thinking it's going to change. We keep thinking it's going to go up to 1,000 or maybe even 1,500. Now, in commercial systems, there is no limit imposed by the NEC. But from a practical standpoint, the limit is going to be around 1,500 volts because there really is no equipment out there that's being manufactured for that size system that's more than 1,500 volts. Most of it's going to be 1,000 volts because that's been the limitation in Europe for a number of years. So they've sort of created a 600 volt line for the US and a 1,000 volt line for Europe. And so those are readily available. What is the largest grid-tied array, assuming its output matches the input, that a load side connected 100 amp rated service panel box currently connected to 100 amps of service from the utility? So what's the largest grid-tied array you could hook up to that system? So what we're talking about here is, let me clean this up. We're basically saying, okay, we've got a service panel here. here's your main, and it's coming in at 100 amps. That's going out to your electric meter. And we've hooked in an inverter. Remember, the inverter has to be hooked in at the furthest point from the main on the bus bar. So we want to hook it up down here in the lower left-hand or the lower right-hand corner. And now it's saying, okay, well, what is the largest array that we could hook up to here? There's some stuff in between, but this is going to be your array going into your inverter. All right, so what's the largest? Well, this is 100 amps, and the service panel box itself is rated for 100 amps. So the first question is, have we already reached its capacity and we can't add any more power into this box? Is that the case? So the NEC says we can actually go to 120% of the capacity of the bus bar, which means we could come in here with a 20 amp breaker. Well, then what size array are we going to have hooked in? So what is the voltage of the power coming out of the inverter?
240.
240 volts, right? So 240 volts times 20 amps going to give us 4,800 watts, right? Everyone clear on that? So you might think that we could hook up a 480 watt, a 4,800 watt array, but because all of these things have incorporated the 1.25 NEC function factor, we would have to divide 4,800 by 1.25, and that gives us something like, what, 3680?
3840.
3840? All right, so that becomes the largest inverter size that you could hook up. Now, because of clipping and things like that, we could have a bigger array. But assuming the array matched the inverter, it would be 3,840 volts, which is one of the reasons why the manufacturers will often put 3.8 kW systems on the market, which seems a weird number, but because of this, you can see why they would. And they also
Sure.
have 7.6 kW systems. And that would be a situation where you have a 200 amp box and 200 amp service coming from the utility. So these are just normal configurations here, which then dictate the size of the inverter that you could hook up and not exceed. So if you had 200 amp service with a 7.6 kW, then you'd have a 40 amp breaker coming in, and you'd still be within the 120% rule.
How can you tell what size box you got? 100.
Yeah, it's going to be right there on the cover. You know, there's a bunch of specifications usually where you can write down the breaker locations and all of that. So all of that's going to be there in the unit itself. It's going to say it's a 200 amp box or a 100 amp box, or sometimes 400, you know, 240 amps, whatever. So that specification is going to be written on that label on your service panel. And then, of course, you'll know what kind of service you're getting from the utility because it'll be right on the main breaker. It'll either be a 100 amp breaker or a 200 amp breaker, typically. But that 120% rule, that's something that people out there in the industry get in trouble with in inspections a lot, because that's something that the inspector is going to look for. And they don't want your ampacity exceeding that 120%. So in this case, it's going to be 3.84 Okay, a standalone system has the following characteristics: a 3 kW array, load demand of 10 kilowatt hours, maximum power draw of 2 kW at any one time, a 1400 amp hour battery bank, nominal battery bank voltage of 48 volts DC, and 4 hours of peak sunlight. What's the minimum power rating required for this system's inverter? Okay, so this is a standalone system. How do we size the PV system inverter for a standalone system? What's the determining factor?
Well, your kilowatt usage.
It's your maximum power draw.
Yeah.
You know, if you can draw 2 kilowatts at any one time, then the inverter has to be sized to handle that much draw. So in a standalone system, it is the maximum power draw that determines the size of the inverter. For a grid-tied system, it's going to be based on the size of the array, because all of the power ends up going from the grid, from the solar panels. In a grid-tied system, all of the power flows through the inverter. It either goes to the load or it goes to the grid. But with a standalone system, the only power that flows through the inverter is that that's drawn from the load, by the load, from the battery bank. So it is.
Why wouldn't it be 2 times 1.25?
Pardon?
Why wouldn't you have to multiply by the 1.25?
For the power draw, you mean?
Right. Yes,
Yeah,
if you're sizing the inverter.
Yeah, it would be a good idea to give it that fudge factor for your inverter. But the question is, what is the minimum power rating? So you could get by with a 2 kW inverter, but a better solution would be a 2.5 or a 3 kW inverter.
Okay.
Because otherwise you'd stress out your inverter. It would still work, but it would be under stress. To determine the maximum panels allowed in a string in a grid-tied array, you must know all the following except the azimuth of the array, coldest temperature, the voltage input specs of the inverter, or the temperature coefficients of the panel.
I don't think you need the azimuth.
Yeah. Remember, when we're trying to figure out the maximum, what we're going to do is we're going to take the delta, the difference in temperature between the coldest day ever and STC, which is what everything's rated at. So we find out how many degrees Celsius that difference is. We multiply that times the temperature coefficient at VOC, because we're taking worst case scenario voltage. So if it's like a 0.39% per degree, we multiply the number of degrees by that. We find out that that system will generate, say, 80% or 120% on the coldest day. Then we take the VOC times 120%, and we find out how many volts. And then we divide that into the maximum of the inverter. Usually it's going to be 600 volts. And that will tell us how many panels we could hook up in a string that on the coldest day ever, it will not exceed the voltage capacity of the inverter. So that's conceptually how that works. The azimuth doesn't even come into play. Which of the following equipment will likely not comply with the 2014 NEC rapid shutdown? So if you recall, in 2014, we began to find that the National Electrical Code said, we want the array to shut down at the array when we turn off the AC disconnect, so there are no live wires going through the house. This was a safety thing for firefighters primarily. But it did say it could be within 10 feet of the boundary of the array. So that allowed us to have electronic devices on the panels, which was the power optimizer or the microinverter at the time, Or we could have a remote disconnecting combiner box, because that would normally be located within 10 feet of the array itself. But a UL listed string inverter, well, that's just a standard string inverter, and that would not work. So in 2014, we could use all three of these. But in 2017, the provision went in and it's shrunk the boundary from 10 feet down to about 1 foot, which basically meant there was no longer the option for a remote disconnecting combiner box. We really now have to put an electronic device on each of the panels, and it has to shut down at the panel. A homeowner in Phoenix, Arizona has a daily load of 9.6 kilowatt hours. She's opted to use microinverters that'll produce 250 watts at STC. She set her altitude at 25 degrees, giving her 6.54 hours of insolation. Assuming she selected a panel that will produce at least 250 watts, and her system is 95% efficient, how many panels is required to meet the load demand? So it's a 9.6 daily, 250, and it's 6.54. So if I can remember these numbers, what we're going to do is the daily load, 9.6 per day. And it was, what was it? 8 point, I've already forgotten, 8 point something. Do you guys remember?
For which? The hours of insulation?
Yeah, that was 6.84,
6.54.
6.54 hours. And it was 95% efficient, right? Were there any other numbers? Okay, yeah, so this is how you would figure it, is
Well, the panels are 250 watts. The inverters produce 250 watts.
250 watt. Okay, so we take our 9.6 kW kilowatt hours per day. We know that we have 6.54 hours per day of insolation, or basically hours of 1,000 watt per square meter radiance. So we divide 9.6 or 9,600 divided by 6.54, and we get
1,467.9
0.9,
watts.
that would be watts, right? So if the system were 100% efficient, that would be the size of the system, but it's only 95% efficient. Now we end up at
1545.
1545.
Yep.
Okay, so that's the size of our array, but each panel is 250 watts. So at this point, we're going to need 6.18 or something like that.
So you need 7.
Yep.
Yeah, 6.18.
So we'd round up to 7 panels. So that's how you would figure that one. The answer here would be 7. And we'd say 7 because it says to fully meet your load. So
Right.
6 would not be the correct answer. Okay, EMT stands for?
It's electrical metallic tubing.
Yeah, and it's very common, very commonly used. The average U.S. home in 2010 consumed 900 kilowatt hours of electricity per month, assuming 4.2 hours of insulation and a 90% D-rate factor. What size array would be required for all power necessary over the course of the year? So in this case, we would take our 960, divide it by 30 and a half,
Yeah.
or as Brian likes to do, multiply it times 12 and then divide by 365. That's going to get you a number.
I'll use yours just so that it lines up. 31.47
31.47 kilowatt
or
hours
475. Yeah.
per day. Then we would divide that by number of hours, so 4.2. That's going to give us
7.49.
7.49. So if you stopped right there, you'd answer that, and you'd be wrong, because that would be the size of the
Get the 90%.
90% efficient. So we divide by 0.9, and we're going to end up at 8.33. And if you used yours, Ryan, of doing times 12 divided by 365, you'd probably end up with a number that's somewhere around 8.4, 8 point, somewhere in there. So you'd probably guess right. You wouldn't find that it's exact, but you get close enough. If you have a wire length of 100 foot in a 90 volt, 8.5 amp D rate, what's the smallest wire you'd need to get a 2% voltage drop? Okay, so this is going to be your voltage drop equation. Hopefully you guys will remember those numbers. I usually keep a sheet of paper here so I can write them down, but it was 8.5 amps, right? All right, so the voltage drop equation is voltage drop equals amps, usually the IMP, times resistance, times twice the distance, divided by 1,000 feet. Because we get resistance per 1,000 feet from the NEC. So 8.5 times the resistance, well, we'll need to figure that, times, and then it was 100 feet, so twice the distance is going to be 200 feet, divided by 1,000 feet, or basically 0.2.
2.
All right, so the only thing that's missing here is the resistance. Well, in the question here,
You can close that. I'll leave the other one. Thanks.
okay, so in the question they have 6 gauge wire with a resistance of 5.51, 8 gauge with 0.809, and 10 gauge with 1.29. So if we can remember those, 0.51 was it? So what we would do is we would just plug the number in. So 0.51 for the 6 gauge. We multiply this, and we get how much voltage drop.
Oops. So this is 8.5 times 0.51 times 0.2 is 0.867.
0.867?
Yep.
All right. And didn't it say that it was a 90 volt system?
Yes.
90 volts. This is our voltage. So it's going to be slightly less than 1%, right? This 0.9 would be 1%.
Right.
So that's okay. That one would work. But the question says, all right, which of these is the smallest wire we can use to get less than 2%? So when we do the same calculation for this, like 8 gauge is going to be 0.809. So we go in here, we just simply change this to 0.809, and we multiply it all out.
We got 1.375.
1.375, and that's going to end up at being, what is it,
Yeah, 1.5.
about 1.5%. And then if we continue this on, you'll find that the last one ends up being more than 2%. So the answer is going to be B, because that's the smallest wire we could use and not exceed 2%. So this is a lot of back and forth, but it gets you your answer. Does that make sense to everybody? You're just doing multiple voltage drop equations to find out which one falls in the parameters. Okay, a cabin sits on a mountaintop in North Carolina. The location has a latitude of 35 degrees north and 4.8 hours of insolation. Daily load of 3 kilowatt hours. Designers installed a 48 volt DC standalone system that's derated for 75%, and the inverter is 95% efficient. Temperature extremes at this location are minus 37 to positive 43. The battery bank provides 2 days of autonomy and uses 6 volt, 250 amp hour batteries to a 60% depth of discharge. Okay, so this is asking us how many batteries are we going to need? This is a battery sizing question. Okay, so what is the information that's given here that's not relevant? Well, we will need to know the daily load.
Right.
We'll need
We
to
don't
know
need
the
the
voltage
insulation.
of the system. We'll need to know that the system has been derated. Well, we don't need to know the system derate. We need to know the inverter derate. And we need to know the battery sizes. So can you guys remember these numbers or write them down or something? You have that?
Yeah, I got it.
You got them? Okay, so I'll go in and I'll start asking you what they are. Because the way you do a battery bank size is the first thing you do is you start with the daily load. So what is the daily load?
3,
3 kilowatt hours
yes.
per day. Now, what we want to get to is amp hours per day. So what do we do here? We divide it by voltage, right? So what's 3,000 watts divided by 48 volts?
62.5.
So it's 62.5 amp hours per day. Well, how many days?
2,
So it's 2 days of autonomy. So now our system's got to be 125 amp hours, right? That's if we could use all of the battery and it were 100% efficient. What is our depth of discharge?
60%.
So we divide this by 60% depth of discharge. So now we're up to
208.33.
amp hours, okay? That's if it were 100% efficient, but our inverter is what, 95% efficient?
219.
219 amp hours. All right, so we need a battery bank that's 219 amp hours to service what we've determined. All right, so, but the question was, how many batteries do we need? Well, what was the size of the battery?
Uh, 125, or no.
250,
250s.
but
So,
that's 60%.
Oh, right.
so how many strings do we need? Just
8,
one,
no,
just one string, right? Right, because the strings, the capacity is going to be fine. We haven't worried about voltage yet. We're just worrying about how many strings of batteries we're going to need. And at
okay.
250 amp hours, that's more than enough to handle the 219. Now, how many batteries in a string? Well, it's a 6 volt battery. It's a 48 volt system. So 48 volts divided by 6 volts 8 batteries per string. Is that right?
Yeah.
So the answer to the question is going to be we need 1 string of 8.
And 8 is one of the answers.
Yep.
Nice.
Yeah. So you could almost have looked at this just by looking at the voltages. 6 volt, 48 volt system. Well, it's going to be either 8 or 24. It's not going to be 1 or 3. So you've eliminated 2 of them just by looking at that. All grid-tied inverters must be rated at no more than 48 volts, be UL 1741 listed, incorporate a modified sine wave output form, or be rated at 125% of the array's output.
UL listed.
Yeah, it's got to be UL. In fact, today they've got to be UL 1741 SA typically in many jurisdictions. SA is the smart inverter. It's the new protocol that and all new inverters are going to be listed as UL 1741 SA, at least if they're legitimate. Okay, it's been determined. Oh, this is one of those string inverter, the sizings, string sizing. It's been determined that a home requires a 6.5 kW array. The homeowner has purchased 26 Solar World 250 panels from her brother-in-law. At her location, the temperature extremes are minus 37 to 43. Her string inverter has an operating range of 100 to 550. Solar panels have the following characteristics: VOC 37.8, temperature coefficient 0.3, VMP 31.1, temperature coefficient 0.45. What is the maximum number per string? Okay, so before I go to work this out, let me just tell you logically what we would be looking at. The first thing we're going to do is we need to know what's the delta or the temperature difference between the coldest day and standard test conditions. So the delta between those, minus 37 and positive 25, is going to be
62.
62 degrees Celsius, a delta there. Then we're going to multiply 62 times the temperature coefficient of VOC, which is 0.3. So that's going to be in the neighborhood of 18%, more or less, right? Well, more. 62, so what, 18.6%?
Yeah.
All right.
Mm-hmm.
Okay, so we know that each of these panels is going to generate 18.6% more volts than it would at STC. Well, what's the VOC? That's the highest voltage the panel is going to generate under STC. So we take 37.8 times 118.6%, and we're going to end up with a number that's 45-ish, somewhere in there.
Yeah, 44.8.
44.8 volts. So on the coldest day ever, that panel is going to produce 44.8 volts. Well, now we got to go and find what's the maximum the inverter can tolerate. Well, the inverter could only tolerate 550 volts. So I'm going to divide 550 by 44.8 volts, and that's going to give me a number
12.3.
12.3. So we round down because we don't want to exceed. And so the answer is going to be 12. Right? So
Okay.
that's the process for the, for the maximum in a string, we worry about coldest day. The minimum in a string, we're going to worry about the hottest day. But that's not our next question. An array of 24 panels, each with an ISC of 8.35 amps, has been configured into 4 strings. The wires are combined in a combiner box. What is the minimum output of the PV output? Or what's the minimum ampacity rating of the PV output circuit? Okay, so it's 8.35. So in this case, what it's asking is if we have an array here, there are 4 strings coming into a combiner box. It was what, 8.35 amps?
Mm-hmm.
And then this is the PV output circuit here. So it's saying, what is the ampacity rating of this? So 8.35 each one times 1.25, which is the NEC safety margin. We do that on all wire. And then for solar, 1.25 before it's regulated by a piece of electronics. So we end up at,
Didn't we do this already?
we did this for
No.
the breakers,
Oh, okay. So that was 13.05.
13.05 amps. Now, because they're being combined in parallel, we have 4 strings. We just
Times
simply
4.
multiply
Got it.
that times 4.
Maybe
That's gonna
52.2.
52.2. So that's the minimum ampacity rating of the PV output circuit. So we look it up on our table. We read it from column 1 because we don't know what the rating is of the termination here or whatever the termination is in the DC disconnect. So we just assume worst case scenario. So I think in this case, what is it? It's like 6-gauge wire or something like that. So we'd look it up on the in the table. So it's 52.19 there with all the rounding. To power a 24-volt water pump with a 12-volt battery, you need to add DC voltage converter, charge controller, inverter, or it can't be done.
So
Can't be done?
just to power it, you just need a DC voltage converter.
Right. Now, what would be a better solution?
Get a bigger, or have the battery be the right size.
Yeah, we just need a second battery and hook them up in series, right? Now we've got a 24-volt battery with a 24-volt water pump. And that would be the solution you'd want to do in a situation like this. But often, like with a electric fence, you might be starting with a 12-volt battery generating 3,000 volts. So you wouldn't want to have a 3,000-volt system, battery. So you have a DC to DC voltage converter. So as you're increasing the voltage, the ampacity is reduced. All right, I'm going to skip over this because it's going to take too much time. We're almost to the end here. But this is just the string sizing for minimum. And the reason we worry about the minimum is we need it to generate enough voltage to turn on the inverter. So otherwise it would just think it's night. There's not enough power. All right, it says here you've configured an electric fence charging 24 hours a day, solar panels rated at 12 nominal volts. When you test the fence, you find it's generating 2,000 volts. What do you need to configure the system? Well, in this case, you're going to need a panel, a DC disconnect, a charge controller, a battery, and a voltage converter, right? There's no AC in this system, so you don't need any inverter. You don't need an AC disconnect. So those would be the components that you would need to do a system like that. If you're wiring a PV array is placed in a conduit and exposed to sunlight, the ampacity rating required for the wire must be adjusted by 1.25, increase, be adjusted if there's less than 4 conductors in the conduit or not exceed 23 amps. So we've got wire in a conduit, it's exposed to sunlight. What is the rating? What's the ampacity rating going to do? And because we don't have enough information, the only thing we know is it's going to have to increase, right? So we're going to have to increase the ampacity rating there. And that's a review of chapter 7. So, and we actually passed that chapter. That's good. So, any questions before we call it a day for today's review session, guys?
I think that's it. I've got another meeting I need to hop into right now.
Okay. All right. Well, see you
Thanks,
guys
Jay.
on Tuesday, and we'll probably jump into chapter 8 and into chapter 9. So, hopefully, if you have
So we
any
need
questions,
8 and 9 for Thursday.
Well, 8's really, really short. So I'll touch.
Okay.
Hopefully, if people have some questions on 7, we'll answer those as well. 7 is the killer chapter. So,
Sounds good.
all right.
Thanks, Jay.
Take care.